All right, guys, I'm sorry. The worst type of lecture is the one where I get up here and I actually do a chalk talk, because that means we don't have the screen, and for some reason this is not responding. I'm sure it's just a little tiny button I have to push someplace, but everything that I'm pushing, playing with, doesn't actually work. So what I'm going to try to do here is I'm going to try to figure out a way to get this screen up. I know I can. I've done it before. And then if I need to write, I will. Yeah, there we go. If I end up, don't you love this little dangly thing in here? Is going to be real fun. So, yeah, I don't know what the deal is, and like I said, it's probably just one button, but I've got this thing set up so that we could actually be doing that. The good news is I'm actually recording myself for the first time ever. Yay. See, I've got the red light there, the red light over here. Come on. And hopefully this will do exactly what we want to do. Now, today's going to feel a little bit fast and furious, but most of you have the slides, so you're going to know where I'm going to be going, and if I need to make a signal like, you guys will know what I'm talking about. What we're talking about today is we're going to be finishing up with vesicular transport, and then we're going to move into signal transduction and how cells talk to one another, which is not terribly difficult stuff. So if it feels like it's fast, don't be frightened. It's not meant to be that way. But what we were talking about last week was we were talking about how do we move material from one side of the cell, or one side of the membrane, to the other one. And so we talked about secondary active transport, we talked about diffusion, we talked about primary active transport, we talked about facilitated diffusion, and that leads us into the two last things, which include vesicular transport and osmosis. And osmosis is the thing that everyone, when they hear that word, they get, I can see it already in your eyes, they're like, I don't want to talk about osmosis. That's what they talk, osmosis. And osmosis is as easy as pie. All right. But first, vesicular transport. Basically, there are different types of vesicular transport. The idea here in vesicular transport is to create some sort of specialized compartment from a membrane to enclose the substances that you want to move from one side of the membrane to the next. All right. That's all it is. And so really, we're talking about movement from either inside the cell to the outside of the cell, or from the outside of the cell to the inside of the cell. And then if you want to make it really complex and scary, you can move from one side of the membrane to the other side, then move across, say, the cell, and then move from the inside of the cell to the outside of the cell. So it's basically the same two movements, just which direction you're going.
Can we think about a vesicle? Can we visualize it as a lysosome where it's got a bio?
Absolutely. So the question is, if I see or if I'm thinking about a vesicular transport, can I think about a liposome? Which is, remember that picture, it was basically a cell membrane which was itsy bitsy teeny tiny. And the answer is yes. In fact, the process of vesicular transport adds to or takes away from the cell membrane. All right? So there are three basic types. Well, actually, there are really two types, and then they split one of the types into two, and then they split it again in a couple more by naming it because of the wonders of cellular and molecular biology. They actually discovered that there are actually some little tiny molecules that are involved that aid in the different processes to distinguish between them. But we're going to keep this simple, so I'm going to go ahead and go to the first process, which is phagocytosis. Phagocytosis, simply put, means cell eating. All right, so when you think of phagocytosis, think I'm eating something. I'm a cell and I'm eating something. And that's a literal meaning. What happens is that the cell comes into contact with some sort of molecule, and that will trigger the cytoskeleton to actually become mobile, cause the cell membrane to move up and outward, and ultimately engulf the structure in a vesicle. And that vesicle is literally inside the cell at this point, and now that vesicle will then be fused with the lysosome, and then whatever's inside that vesicle will be destroyed, and whatever the components are going to be used and for whatever need that the cell has. That's phagocytosis. It's a specific attack on something and bringing it in. And really, when you think about that, I mean, you've all heard of the cell, the macrophage, right? You know, macrophage is big eater. And what does a macrophage do? Phagocytosis. So there's an example. I'm going to get angry at this in a moment. All right, so that's in essence what phagocytosis is. It's basically going out, it's first recognizing the substance and then activating the cell to engulf and then bring in this vesicle filled with the thing that you've actually engulfed and then destroying materials within. The other types of endocytosis are broken down based upon what is being accomplished and what molecules are involved. And so this is endocytosis, bringing things into the cell. And so the first type is called pinocytosis, which literally means cell drinking. which in the days when they were starting to name this stuff, you had phagocytosis, and then you had this non-specific form where it looks like you're taking the cell membrane, you're going out, and then you're grabbing a portion of the extracellular environment inside a vesicle. And it's non-discriminatory. It's just whatever's there is there. And you bring this vesicle inside, and you use whatever fluid or whatever molecules or whatever is found inside. So that's the cell drinking, pinocytosis. All right? And then they distinguished phagocytosis from another type of endocytosis, which is specific, which was called receptor-mediated endocytosis. Now, in this case, what's going on is you have an area on the cell surface that's kind of it's not even necessarily an indentation, but ultimately it will become that. And what you have are, basically you have receptors all over the place. All right? And when these receptors get bound by a specific molecule, these receptors then localize to a region that contains another molecule called clathrin. All right? See, this is why I'm such a great artist and why I prefer using the slides over this. And so what happens is all these receptors begin migrating with their ligand. And when that happens, when you get enough of them, then what's going to happen is that the membrane then, again, it kind of goes up, and then it encloses and creates this vesicle with the receptors plus all their ligands. And what you've done now is you've brought a very specific molecule into the cell. Now what you're going to do with that molecule is going to be dependent upon the molecule. All right? You can use this as a method to bring in a very specific substance that the cell needs, or it could be a way to bring in signaling molecules, or any number of things. All right? And then the third type is called podocytosis. All right? P-O-T-O. And this was actually back when I was in school, which, you know, Age of the Dinosaurs, papyrus, that sort of stuff. We didn't even have this type. So, you know, it was kind of new to me. And really all this is this, again, this is like receptor-mediated endocytosis. The difference is that instead of using specific receptors that are kind of floating all around, instead you're using the concept of the lipid raft. And so remember what we talked about, we said the lipid raft is basically these sphingolipids that kind of accumulate together, and then they have specific proteins that are kind of associated, and this whole complex kind of moves around within the context of the cell membrane. And so what you're talking about here, this caveoli, this small pockets, I guess I need to put my pen here. These small pockets have these lipid rafts, and so it's very similar, it's just different molecules and markers that are involved. All right? Now, typically, podocytosis is used to transfer molecules through a capillary wall. All right? And so you can imagine you have this endothelium of the capillary, which is the name of the cells that make up the walls of the capillary, to move from the plasma to the interstitial space. There are different ways to do it, but one of them is to go through the cell, and so you use calveoli to pick up what's floating around in the blood, specifically, some specific molecule. You create this vesicle, and then you move it across the other side and release it on the other side. So that would be an example of podocytosis when you pick this stuff up, not when you're releasing on the other side. Yes, sir?
With respect to the receptor-mediated endocytosis, the presence of clathrin, we need to know anything more than that clathrin is present when it gets implanted.
That would be, at this point, that's all you're going to need to know. When you take cell biology, they'll go into a little bit more detail. Yeah, there's enough to learn in this class before I start hitting you with all the molecular biology. All right. So these are the three different types of endocytoses, and why phagocytosis was kept separate, I don't know. Somebody who's important decided that I'm going to keep this one separate. All right. But you can see, what we've done now is we've brought materials into the cell. Different ways to bring materials into the cell. Now, I understand that not everybody has my slides. I understand that sometimes I talk fast, and I'm not going to be walking up here to draw on the board all the time. If I say something that makes absolutely no sense to you, even if you have the slides, and you need to say, wait a second, I don't get it, please raise your hand. Okay? Because there we go. That's what I like. Phagocytosis technically has been separated away now. Now, am I going to ask you a question on the test that says, is phagocytosis is like endocytosis or is a process? No, that's semantics, and I'm not going to do that. All right. You know, there's plenty of ticky-tacky things I can go after, and I don't think that's going to be one of them. And there are times if I actually say something I'm not going to test you on in class, and I actually test you on it on the test, you can come to me and say, remember you said that, and I'll go, yeah, I have so many questions that I write that I don't remember what I told you and what I don't when I'm doing it. So, all right, so I'm going to avoid that. All right, now there's a, yes, all right, let's go here, and then I'll come here. Raft, like picture sitting on that. Yes, yes. I'll start clearing it up. That's why I have the Diet Coke. And whoever brought it to me, thank you. Let me go here. Say it again. I want to see. Where was the you're welcome? Thank you. Yes.
What did you say was difference receptor mediated and phagocytosis?
Receptor mediated phagocytosis? Well, phagocytosis really deals with, and that's actually a good question, really deals with very large particles. I didn't actually point that out, and that's a good point. So when you're talking about phagocytosis, you're literally going to be taking in large particles, either large molecules or even larger cells. So you can think of it like this. A macrophage, one of the things that it does is it hunts down those nasty little bacteria that try to find its way into your body. And so what you'll do is that when it comes into contact with the bacteria or is actually receives a chemical signal from the bacteria, it starts hunting it. And there's actually great videos on YouTube where you can actually see, for example, an eosinophil chasing a bacteria through cells. It's actually the funniest thing. Yeah. Where was it? Yes, sir. All right. The question is, when does pinocytosis occur? It occurs all the time. And really what you're doing here is you're just kind of sampling in the environment. Now, does that mean you're really just kind of saying what's going on in the world? No. It's actually you're trying to bring in material into the cell, you know, that you can take advantage of, but we're not talking about specific molecules that you're searching for. You know, the idea, if you take in a protein, you can break down the protein and use the amino acids, that sort of thing. So it's a very non-specific way to do it. There's no receptor involved, no recognition of any specific molecule. It just happens. Yeah. Everyone good so far? Yes.
Receptor mediated endocytosis, the receptors only sort of get together in the skin and once the ligand is found.
That's correct.
Okay, and meanwhile,
yes, so you can imagine it's like a bunch of you guys just kind of bopping around, and then finally someone gets something in, well, I don't know, let's say a Starbucks card, and where do you go? Straight to Starbucks. All right, and that's in essence what's going on here. They are free within the membrane, and actually when they get bound, you know, even though I drew this little kind of Y-looking thing, you got to recognize that there's a change in shape, and so that causes a change in its functionality in terms of the receptor. And so part of that is it will cause it or force it to migrate towards and actually bind to the clathrin. Now what happens is when you're dealing with these vesicles, once they form and once you're in, you know, there's going to be modification to this vesicle, so you can actually recycle the clathrin back to the cell membrane, and then this can fuse with the lysosome or any other sort of vesicle to either break down or transfer or use the materials that's been brought in. All right, so you got to understand that, you know, while we're looking at this in a real simple way, there's actually a lot of stuff that's actually going on in terms of the recycling, in terms of using the materials in here. All right, but notice what we've done. We've created a specialized compartment in either of these cases. And so the reverse of endocytosis would be exocytosis. And so you can think of it this way, is most cells are producing materials that are going to be used outside the cell. Okay? So we're releasing proteins, for example, you know, to the external or out into the bloodstream to be transferred, or you're just making, you know, plasma proteins. That's what the lipid does, or sorry, the liver does. And so here, what you're trying to do is you create a vesicle, and then whatever inside that vesicle will then fuse up with the plasma membrane. And so when it comes into contact with the plasma membrane, based on its own structure, is going to associate in such a way that all heads point towards liquid and all tails are away from liquid, so it just fuses and you release the contents out. Now, you can think about this in real simple terms if you think of when I'm making proteins, or get rid of this thing. Oh my goodness, these people just never stop writing, do they? All right, fine. Let's go over here. Might as well be in the middle of the classroom. Like you guys will ever use physics ever again. I'm lying. You all will take the MCAT. Oh, I'm sorry. Yeah, actually, it's not true. I actually once, a long time ago, I asked an anesthesiologist, I said, "Did you ever use this?" He says, "Absolutely." And he said, "See this pole?" He lifted up the pole with the IV on it, said by raising up the pole, that creates a greater force to drive the fluid down into the patient. There's physics for you. All right. So when we're making a protein, proteins are more or less, not all proteins, but many of the membrane-bound proteins, or the proteins that are going to be released, or at least are created down here at the endoplasmic reticulum. So here's my nucleus, here's my endoplasmic reticulum, right? And then what happens is we get vesicles that get formed and then transfer to the, remember, Golgi. And then from the Golgi, you create more vesicles, and then those vesicles then are being fused with the membrane. And so what we're doing here is part of this endomembrane system is we're creating more membrane and we're moving molecules in a very specific direction, right? So exocytosis is I can have molecules that are over here in this little vesicle right here that I'm just going to release out here once this thing fuses, like so. So I'm releasing my materials. Or I can have receptors. I know this is little itsy bitsy teeny tiny, and you can't see that they're little tiny Y's again. And then when this stuff fuses, what I've done is now I have my receptors pointing in the right direction. I've added new membrane, but it doesn't matter that I'm adding new membrane because why? At the same time, I have endocytosis taking place. All right? So exocytosis and endocytosis are occurring all the time. This is a way to get material out, with regard to exocytosis is a way to get material out of the cell or to put proteins, for example, in the membrane. Now, there's a great picture I have here, a real large one that shows you the two processes side by side, and so you can see them together. Now, cells just don't move things in and move things out. They also move things through cells. All right? This is a way to move materials, or this process, which we refer to as epithelial transport, is a way to move materials from one side of the cell to the other. Now, we can do this in one of two fashions. We can actually go in between cells. So if we have a cell here and a cell here, I can move in between them. All right, this is called paracellular transport, and this is just a sneaky way of going between or going through cells. So you can imagine on one side of the cells, I have, say, the lumen of an organ. On the other side, that's interstitial space. And so if I'm trying to move materials from the lumen inside the organ, that's the hole, the space, I can sneak in between the cells if I'm small enough. All right, but most things have to pass through cells. Most things are too big to sneak in between the cells. And usually you have tight junctions which aren't particularly leaky, although there are leaky tight junctions. But basically what you have is there's only one way to pass through. All right, and so this is when you're going to use that transcellular transport. All right, and so the idea here is you're going to have some sort of mechanism that's going to allow you to move materials into the cell, and then on the other side of the cell, some sort of mechanism that's going to allow you to move materials out of the cell. Now, what processes are you going to use? Well, whatever's available to you. All right, so it could be primary active transport, it could be secondary active transport, it could be diffusion down through a channel, or it could be facilitated diffusion. It could be carrier-mediated transport. It could be vesicular transport. Now, just using that first group, the stuff that we learned last Thursday, you can think about it like this. If I'm moving things from one side of the cell down through the other side to the other side of the cell, that process, there's two of them, right? So here's my cell. All right? I have one process here, I have another process there. And what that means is from moving one solute here to here is either going to be upstream or it's going to be downstream. But whatever it is, to move from here to here is going to be the opposite. Okay? So just as an example, using a real simple model like sodium. Sodium moving from the digestive tract into the cell would be a downstream process, right? You'd have, let's say you went and ate a bunch of French fries. Make it easy for you to visualize this. All right? So you have a bunch of French fries, that's a whole bunch of salt. You have a lot of salt in the digestive tract. Salt is high here. and it's low here. So you can see sodium moving into the cell would be a simple process moving down its concentration gradient. But if I'm trying to get salt not just into the cells that line the digestive tract, I want to get that salt wherever it needs to go throughout the body. That means it still has to come all the way through the cell, and to get it out here, it's going to be an active process, right? Because the concentrations of salt in the interstitial space is much, much higher, or at least sodium is much, much higher. So if this is passive, this has to be active. And the converse is true. If it's active to come through this way, then coming out this way would have to be passive, right? And it's all dependent upon what sort of concentrations. And the example I've given you on your slides shows glucose being moved from the digestive tract into the interstitial space, which will ultimately go to the blood. And so here, moving glucose from the digestive tract into the cell is an uphill process, right? Because cells have a lot more glucose in the surrounding environment. Doesn't matter if you drank a full soda, right? And I'm not talking this stuff, I'm talking the real stuff, right? It doesn't matter because there's always going to be more glucose in the cell, so you're moving glucose uphill, all right? Now, in the case of what we're talking about, moving glucose uphill, in this case, we're using secondary active transport, right? And then moving glucose out into the bloodstream, well, we have nice, simple glucose transporters that will allow that to happen, and you're just moving downhill once again. So this process of moving things across cells, epithelial transport, requires both an uphill and a downhill component. Now, you can do this also with vesicles. And so, again, when you're talking about moving materials with vesicles across cells, we just refer to this process as transcytosis. So if you ever hear that word, oh, it's like I'm using endocytosis and exocytosis to move things from one side to the other. And so the example I've shown here is using podocytosis to pick up the materials from one side of the capillary endothelium and then moving it out into the interstitial space. All right. So this is just kind of a little bit of vocabulary. Now, how many of you guys are scared of the word osmosis? You've learned it, you can regurgitate it on a test, but you really don't know what it means. I am. I can promise you I did not learn what osmosis was until I was in grad school, probably my second year of grad school, which is really kind of embarrassing to admit. But it's okay to admit our shortcomings because it only makes us stronger. Why? Because people laugh at you. Now, osmosis is not tough. For those of you who think it's tough and are scared by the concept of osmosis because it gets kind of confusing, osmosis is easy. It's just diffusion. And really what it is the diffusion of water down its concentration gradient. All right? So water moves from an area of high water concentration to an area of low water concentration. Pretty simple, right? So it's the definition of osmosis, except for one thing. No one ever talks about the water when they're talking about osmosis. They're always talking about what's in the water, which is the solute. And this is why it gets so confusing. So let's make our lives easy. Ooh, I like this. So let's pretend we have a solution. All right? I'm going to actually create two solutions. All right? In one solution, we have lots of water. And here we have very little solute. Now, notice I didn't put percentages, I didn't put numbers, I'm just giving you concepts, right? And then over here, we have less water than we have over here. I'll just do it like this, and so here is our solutes. All right? Now, in relative terms, could you see that the quantity of water in side A is greater than side, let's screw things up, Z. You thought I was going to say B. Can you see that water is greater on side A than side Z? Yes. And then, if you look at the other material, the solutes, which has the greater solute? Z, right? So, the way that osmosis is usually defined, it says water moves to the area of greater solute concentration, which just screws everything up. Think in terms of one substance or the other. You're moving water from high water concentration to low water concentrations. Why is a low water concentration? Just so you remember, it has a high solute concentration, right? Now, Usually when we're talking about osmosis, we're talking about some sort of membrane, right? So we usually see either the horrible U thing. It has a membrane that's semi-permeable. You know, it's permeable to water, but not permeable to the solute. And it usually starts off and says, look, here you got your solution. Over on this side, over here, you've got tons and tons of solute. Over here, you have very little solute, so what's going to happen? And then that's when your brain starts going, I have no idea, because do I deal with the solute? Do I deal with the water? Do I deal with the little polka dots? I don't. What am I looking at? Is that about right? And so you confuse yourself on the exams, and you end up with a whole bunch of issues. Do you have a question? Or you're just going, he's going to get someplace here with this. All right. So all we got to do is we just got to look at this again. What do we have? If the little dots represent solute, we have more solute over here than over here. That means we have more water over here than over here, so water wants to move in that direction. And so that's what happens. And it will keep moving in that direction until we get some sort of balance. What balance are we looking for? Concentrations. So if I have 1 million molecules of water over here and 500,000 molecules of water over here, I'm going to try to find some sort of balance, 750,000 molecules. But there's a problem. And this is where everybody gets screwed up again. Because what we don't remember is that with any fluid, we have hydrostatic pressure. All right? Hydrostatic pressure is the pressure that's being exerted in all different directions by the fluid. Right? And so every time a molecule of water transfers over that semi-permeable membrane, and every time we get another molecule of water, we've increased the hydrostatic pressure. And as we increase the hydrostatic pressure, it becomes harder for the next molecule to come over. And then the next molecule, and the next molecule. The way I like to think of this, it's like trying to stuff people into a phone booth. Now, many of you guys don't know what a phone booth is because we got rid of them a long time ago. But back in the 60s, this was something that was popular among college students. Yeah, stuffing people into phone booths. All right? But try it sometime. Try to find I don't know, what are those? The Souls? Is that the car? The key? You have a Kia Soul? All right. How many people can you fit in that car? Have you ever tried? You can fit a lot of gerbils in it, you know, because they're cool. I think they're hamsters because they don't have tails. Right? But try it. Take your car and, say, guys, we're going to see how many people we can fit in this thing. Like a clown car. And at a certain point, the next person to go in makes it that much more difficult for the next person after that to go in. Does that make sense? And that's what's going on over here. The hydrostatic pressure for each molecule of water that's moving down its concentration gradient that goes in creates a stronger pressure on this side, which is going to prevent the next one to come in. And that point where the pressure becomes so great that the next molecule that goes in pops right back out is a point where we've reached osmotic pressure. In other words, that's the pressure that counters or opposes the movement of water down its concentration gradient. Does that make sense? So using the Kia Soul example, once you get student number 18 in there, you're going to reach the point where the next person you push in is going to cause a leg to pop out. Right? Yes. So what I'd say, the osmotic pressure is, simply put, the pressure that opposes the pressure, it's the pressure that opposes the movement of water down its concentration gradient. I think the exact terms I used was the opposing pressure necessary to completely stop osmosis, which is textbook talk. Did that make more sense? The pressure, it's the hydrostatic pressure on the receiving side that opposes the movement of water down its gradient. All right? So far, you with me? Does that seem a little bit easier? I mean, water diffusion. I mean, how hard is that? I mean, why can't they just say that in chemistry? It's water diffusion. Oh, okay. That makes sense. No, they go down the whole solute thing. That just confuses everybody. Any questions about osmosis? Yes. Absolutely. And that's perfectly fine. In fact, that's the strict definition of it. All right, is water moving to areas of higher solute concentration. But because of the way that the language is used, it does become confusing to, because then you have to start thinking, all right, what is my solute concentration? Because very often what you'll see is you have a solution of 100 milliosmoles, over here you have a solution of 20 milliosmoles. Which way is the fluid going to move? And then you're sitting there going, it's just like, just remember, there's less water in the 100 milliosmoles, there's more water in the 20 milliosmoles, which we're going to get to in just a second. So you just have to remember, water, we're talking about water movement, we're not talking about those solutes movement. All right, here and then over here. Yeah.
Is that like pressure to stop like osmosis from happening, or like pressure that stops it after it's like moved all the water?
Well, remember when we were talking about diffusion, we said that there's a net diffusion. So when you have even when you reach equilibrium, molecules are still moving in the same. And so that's the same thing with osmotic pressure. Osmotic pressure is that pressure that stops the movement or the net flow in the direction of the osmotic gradient. All right. In other words, we're not stopping the movement of molecules. We're just preventing molecules from moving in the same direction. So that we're basically stopping that diffusion of water. Does that make sense? So it's the hydrostatic pressure that stops osmosis, but molecules are still moving. Yes. Yes. Well, no. All right, so in this particular example right here, right now in this particular picture, what does the hydrostatic pressure look like from side, ooh, let's make up some new ones. Oh, we'll just call this side L and side Q. Because if we saw A and B all the time, we'd be bored. See? So what's the hydrostatic pressure on both sides? Are they equal? Is one greater than the other? What do you think? They're equal. Right. Right. I mean, you know, we don't know anything about the solutes, so we have to make some assumptions right now. And so the assumption is that because I've more or less made these equal, that the hydrostatic pressure should be the same. Now, let's set this solution out for a little bit and let osmosis take place. And so what ends up happening now is now we're at this point. Now where's the hydrostatic? Is there hydrostatic equal now? No. It's greater on this side, right? And water would continue to move this way until this pressure becomes so great that it prevents anything from moving forward. Does that make sense? Yes. Uh-huh. For our purposes, yes. Even though I can't draw equal things to save my life. Yeah. Okay. Yes, and then back over here. Well, so the term hydrostatic pressure means the pressure of a fluid. So in this case, it is a hydrostatic pressure because it's a fluid. So the osmotic pressure is the hydrostatic pressure that stops osmosis. That's the definition. Yes. That's right. Right. So, can of soda, which it's not, it's a bottle of soda. I know if this was the internet, I'd be spammed for an hour. Is there a hydrostatic pressure in this thing? Yes. It's going in all directions. Would you agree? Except for up, right? And if I poked a hole in this, what would happen? Would the fluid come out? Yes. All right. Why? Because the hydrostatic pressure is driving the flow of the fluid out. So you guys understand fluid dynamics in a very basic, rudimentary sense. So that's really what we're saying. When we say hydrostatic pressure, it's just the movement of that fluid trying to escape within the confines of its container. Yes, sir. That's right. I mean, I'm going to see if I can do this. Imagine there's a molecule of water over here and 999,000 molecules of solute. And imagine over here there's 1,000,000 molecules of water and 1 molecule of solute. Which way is the water going to go? It's going to keep going this way until you reach some sort of equilibrium, right? Exactly. You know, it's going to be dependent upon, you know, the absolute molarity or the osmolarity of the systems. All right, but you're absolutely right. You can look at something and just say, you know, if you put like, here's a block of salt here's pure water. Is it just going to reach equilibrium? No, because remember, you don't have solute moving the other direction, so water is going to be drawn in until we can get equilibrium between the concentrations of water. But at some point, that pressure is just going to become too great and say, no, I can't do this anymore. Yeah.
And so the first bullet point on this slide, is that describing what it's like?
I'm presuming it's on the first one, the net diffusion of water across a membrane. Is that what it says? Yes, yes, yes. So what we're trying to say is, what I'm trying to say there is that water is going to move until something opposes it, right? So in our little container over here, the pressure of the plastic on the side is greater than the hydrostatic pressure inside the soda, right? I mean, and if it wasn't, we'd have soda all over the floor. And so what we're saying is here is water wants to diffuse down its concentration gradient, just like everything else does, all right? But what's going to happen is that ultimately there's going to be a pressure that opposes it or prevents it from going down its concentration gradient. Now, I could bring up about 7 people up here, or maybe 8 people, try to get them balanced, and do a tug of war, And then as people are moved from one side to the other, we're going to create more pressure that's going to favor movement one way or the other. Does that make? That's a terrible example. That's why I didn't do it. So just erase your brain from that one thought. Yeah, we'll stick with the Kia. Osmotic pressure, everyone okay? All right. Yeah, we're moving real slow today. Now, you've seen this term, or you've heard this term before, but you probably never thought you'd ever use it. It's the term osmolarity. You've heard of molarity, you've probably heard of normalcy, which you probably confuse the hell out of you, and that's fine, because I still don't understand it, quite frankly. But we have something we use that's called osmolarity, and what osmolarity does is it describes the number of particles in solution. It does not say anything about what the particles are, it just says the number of particles in solution. So if this room were a solution, and all of us, all the living things in this room were particles, we could count up the number of particles and determine the osmolarity of the room. Now there's probably little tiny flies and other little tiny things living in the room, bacteria that you brought in here in your bags and stuff like that, and then that increases the relative concentrations, right? And so osmolarity deals with not what, I remember I just said living things. Osmolarity deals with the number of particles. So, when you think of something like glucose, glucose is a nice, happy, stable molecule. And you put it in solution, it's going to stay a happy molecule. And so, one glucose molecule equals one glucose molecule. So, when you put it in solution, let's say, well, it's going to, whatever you put in is going to equal its osmolarity. But something like sodium chloride, which would dissociate into the sodium molecule and the chlorine molecule, for every sodium chloride you put in solution, you end up with 2 molecules. And so the osmolarity is not equal to the number of molecules that you started with. It's twice, double. So osmolarity deals with particles. It doesn't deal with what the particles actually are. Now the reason I bring this up is because we're going to refer to things in terms of osmolarity a little bit later. And so I don't want you to be going, I don't know what osmolarity is. You do. It's just solutes. It's particles. It doesn't say anything about them. Now the other term I want to just go over just briefly deals with tonicity. Isotonic, hypertonic, hypotonic. And you look at those words, you go, yeah, I got that. And then on the test, everyone misses the questions because they overthink everything, right? And so the term hypotonic, isotonic, and hypotonic are pretty simple, all right? You've got hyper, which means more. Okay, I'm just going to say greater than. We got iso, which means same, and hypo, which refers to less. So we've got that part. That means we have to deal with the other half, the tonicity or tonic. And what that refers to is solute. All right? So when you see a hypertonic solution, what they're saying is that this has more solute than what I'm comparing it to. Does that make sense? That's where everyone gets screwed up, is the relativity. All right, I put a cell in a hypertonic solution. That means the solution is greater than the cell. It has a greater solute concentration than the cell. So remember, what you're referring to, is it a hypertonic solution or is it a hypertonic, cell? And it's usually going to be referring to the solution. I'm putting something into something else. It's a relative term. All right? So tonic just means solute. So more solute, same solute, less solute. So when you see that term hypertonic, automatically think I'm talking about whatever's in the solution. I'm not talking about the water. So if you have a hypertonic solution, what do you know about the water? Hypertonic solution, it means the water is a lot less. It's a Z. All right? And notice, it's relative. All right? Z is hypertonic relative to A. All right? A is hypotonic relative to Z. And that's the fun part. The osmolarity, absolutely. Right. But osmolarity is really an actual number, where if you say this is hypertonic, you say a hypertonic solution, it doesn't talk about an absolute number. So this is something that you can count. So we'll say like the body has a concentration of 300 milliosmoles per liter. And all of a sudden you're going, what? I've never heard of a milliosmol. Well, you have. It's osmolarity. You see? Notice it didn't say what the particles were. It just said number of solutes in solution. Yes?
When you talk about non-penetrating solutes,
Mm-hmm.
it
Right. It doesn't. Absolutely. Right. So when we're talking, so you'll see if you look at the slide that said a non-penetrating solute, really what we're saying there is this is the solute that's found in solution and is not going to permeate or pass through the plasma membrane or whatever membrane you're talking about. All right. So I think that kind of summarizes what I wanted to say about transport. That only took us 45 minutes with no slides. What that leads me into is what I want to talk about, hopefully, I know I'm not going to get through everything, but I want to, I know I'm not going to, is I want to talk about how cells talk to one another. Now, in order for us to understand how cells talk to one another, we're going to need to understand a little bit about how our bodies deal with electrical currents. All right? Now, you are electrically neutral. You cannot shock me, I cannot shock you. Well, that's a word that has many meanings, but you cannot sit there and say, and get me. All right? We are electrically neutral. All right? We can build up a static by shuffling our feet on carpet and stuff, but that's not you. All right? Those static forces are external to you. Now, what that means is when we say we're electrically neutral, what we're saying is that they are basically the same number of positive and negative charges inside your body. All right? So for every positive charge you have, there's a negative charge. The problem is that not all these positive and negative charges are in the same compartments. Now, here's some things you should remember, right? Positive charges and negative charges are attracted to one another, right? So if you have them in separate compartments, they're going to try to find a way to get towards one another. All right? The other thing is that when I take two charges that are attracted to one another, it takes work to keep them separate. And if you've ever had to host, and you guys are far too young, but if you've ever had to host a high school dance or chaperone one, you've learned this principle. Couple goes together, please separate. That's work. Now, the way that separated charges are going to move towards one another are through conductors, and in our body, the conductor in our body happens to be water. That's the way that ions move around. And the way that we keep these charges from moving towards one another is we keep them separate by insulators, and the insulators in our bodies happen to be the plasma membranes. All right? And so, if we're doing work to keep things separate, then what we're saying then is that the plasma membrane is doing work to maintain or keep these charges separate from one another. Now, what happens is, if you can imagine, in every compartment in your body, you have positive and negative charges, but you have some charges that are unmatched. And so what happens is that anything that is attracted to another charge will come together, all right, and create some sort of cute little couple. And then what you're going to be left with are these lonely charges. They're just sitting around in their compartments, pining for their opposite charge. And then in the other compartments, again, you have all your positive and negative charges come together, and then you have some leftover charges that are left all alone, pining for their opposite charge. And so what happens is that if you have a membrane, you have positive charges that are all alone over here, and you have negative charges that are all alone over here, and they begin to move towards one another. And they localize around the plasma membranes. Now notice, they didn't come together because they're separated by the plasma membrane. All right? But they're still attracted to one another. And what we have here is, if given the opportunity, would those charges come together? Yes. So if I put a hole in the plasma membrane, then we would see the positive charges moving towards the negative charges. And that's how we always describe movement, as positive towards negative. If I have 50 positive charges over here and 10 positive charges over here, do I have a gradient? Yes. Because what we could say is that this side over here is more negative than this side over there, right? Over here. And so what you'd see, you're going to see a movement of positive charges down its electrical gradient. Aha! See what I said about these gradients? You're going to see this term over and over and over, and you're going to be so tired of it. All right. Now, the thing is that all of our electrical charges are really ions. And we've already described ions, haven't we? We've said that ions are basically little tiny molecules, or in some cases, atoms, right, that carry a charge. And so if I have a whole bunch of atoms over here and fewer atoms over here, what do I have is a chemical gradient. And so we can have both an electrical gradient and a chemical gradient simultaneously. And we refer to this as an electrochemical gradient. All right. Now, the significance of this electrochemical gradient allows us to understand a principle called the resting membrane potential. What the resting membrane potential is, simply put, is that difference in charge across a membrane. Now, first off, notice what I said, it's across the membrane. Is the membrane itself charged? No. All right. So whenever you see a membrane, don't think it has a charge. It's the localization of those free and independent, lonely, sad, pathetic little uncharged molecules localizing, looking across the membrane going, oh, if only I could be with you. Right? That's what's going on here. And so, because they're being separated by a membrane, and that membrane, we said when we separate charges, is doing work, what we have here is potential energy. And so the resting membrane potential then is the potential energy bringing those two charges together if they could come together. All right? And the resting portion refers to what's going on with the cell. The cell is doing nothing. All right? It's at rest. All right? So the resting membrane potential is the constant membrane potential of our cells when they're not doing anything. Now, there are many different molecules that are responsible for the resting membrane potential. Now, I have a little slide here that shows you a list of them: sodium, magnesium, potassium, calcium, phosphates, chlorine, bicarbonate. And then I have this symbol here that no one will recognize because it's this. And that's just an anionic cellular protein. Yeah, it's not a real chemical, so you'll notice it's not up there. All right. So this is a negatively charged protein. And these are different molecules or different ions that can play a role in creating a membrane potential. Now, of all of these things that are on the big list here, the ones that are important include sodium, chlorine, and potassium, as well as this anionic protein. All right. So what we're going to do is we're going to use these to help us understand how our resting membrane potential is actually established. And again, this is not the most exciting stuff in the world. I know this is not the most exciting stuff in the world, but once you understand it, you'll never ever forget it until after this class is over. And then, well, it'll make sense. It'll help you understand what's going on. All right. So first off, what we're going to do is we're going to look at potassium. And we got to recognize, remember on that very first day or second day of class, I basically gave you or showed you a graph that had the different ion concentrations both inside and outside the cell. Well, that's kind of what we're doing, what we're playing with right now. So what we have is we have a cell. Inside the cell, we have a bunch of potassium. And we have a bunch of anionic proteins. And so what we have here is a nice little balanced little system. And outside we have sodium. I'm just going to draw it over here, even though it's everywhere. And I have a bunch of chlorine. Everything's nice and balanced, and the world is a happy place. All right? But one of the things we learned is that there are channels, and these channels are specific. And if we create a potassium channel in our cell, what's potassium going to want to do? It's going to go out. Why? What type of gradient? Chemical. Right. Because if you look at this, everything's nice and balanced electrically. So potassium is going to go out because it's moving down its concentration gradient. And when it does so, what happens to the environment in terms of its charge? It has, well, the inside has lost a charge, you're right, and outside has gained a charge. All right? So the movement of ions down their chemical gradients will result in a change in the electrical gradient as well. And notice that these two forces are in opposition to one another. So the chemical gradient is in this direction, but the electrical gradient is in this direction. Because what's going to happen? When this potassium leaves, we now have an extra charge. We only have a channel for potassium, so what's this potassium going to want to do? It's going to want to balance out that negative charge. Does that make sense? So it's just moving down its electrical gradient. Now notice, all we're doing is we're focusing on one molecule here. And I said there are several molecules that are involved. All right? But this is the first step in understanding everything that's going to be going on here. Yes?
I know you get potassium wants to move back into the cell to balance that negative charge.
Mm-hmm.
There's more potassium inside the cell. Now it's going against the chemical gradient and it's going along with the upward.
Very interesting. So what? You definitely could do that. Let me challenge you with this. What happens if I take this away? What's our relative charge on the inside now? -2. Right? Because if I started off with 4... Oh, wait. Yeah, I meant to go the other direction. Here we go. There. So I start off with 4 potassiums and 4 or 5 anionic proteins. So I start off at a negative charge. Now, is potassium still going to want to leave down its chemical gradient? Do it this way. Remember, just focus on it. If I have 4 potassiums here and I have 0 potassiums here, is potassium going to want to move in that direction? Yes. Great. So I let that happen. So now I have 3 potassiums over here and 1 potassium over here. What's potassium going to want to do? It's going to want to go that way. Oh, look. Balance. Except for one thing. If I've done this, where I now have 2 potassiums, what has happened? I've got a whole bunch of negative charges. I've got 3 negative charges that are very, very unhappy and very unsatisfied. What are they doing? Please come back, Mr. Potassium. Please. And what's potassium doing? Because out here, now we have 2 extra positive charges. What does potassium want to do? It wants to go back. Because what we have now is we have a difference of, if this is 2 positive and 3 minuses, we have a difference of 5 charges. All right? And so what we're saying then is that there's going to be a pull to bring back potassium to try to balance out the discrepancy between the charges. All right? So the chemical gradient favors movement in one direction. The electrical gradient favors movement in the other direction. And at some point, these two things, the electrical gradient and the chemical gradient, will reach some sort of balance. Where that balance is? Well, we can figure it out using a formula. Are we going to have to do math on the test? No, because math sucks. But we should be aware of how we should be able to do it. And it's through a formula called the Nernst equation. So let's erase this ugly, nasty, horrible looking. Yes. Not always. It's way more complicated than that. Sometimes it favors, chemical gradients will favor the electrical gradients as well. But the way that our life is based is it creates this and uses and takes advantage of this. All right. So the Nernst equation is this really ugly formula that says the equilibrium potential of whatever the chemical is equal to 61 over Z times the log of the concentration of the ion outside the cell over the concentration of the ion inside the cell. Now, the 61 log is based on a whole bunch of little constants that I can't remember off the top of my head. So, noble gas law, universal gas constant, absolute temperature, Faraday's constant, plus also conversion of the natural log to the log. All right. Which one? This one right here? Oh, it's ion concentration outside the cell versus the ion concentration inside the cell. All right. Now, once again, you're looking at this going, oh crap, there's math here, and I've got to do the math. Well, no, I'm not going to make you do math, but it allows you to see what's going on. The Z refers to the valence, and you all remember valences, right? You all took chem, and so you remember valences. So potassium has a valence of +1. Sodium has a valence of +1. Chlorine has a valence of -1. See, I'm not going to do anything hard here. Calcium has a valence of +2. See, so you'd have to think when you see calcium, but we're not doing that. All right. So all we got to do then is know what the concentrations of these ions are both inside and outside the cell. And if you look at a chart, which you can see, I think 3 slides before, it actually says on that slide where it's actually 2 slides before. It says the concentration of sodium outside the cell is 150. The concentration of sodium inside the cell is, 15, thank you. And then I'll do it this way, sodium, and I'll do potassium over here. Concentration of potassium inside the cell is, this is outside, this is inside. So the concentration of potassium outside is 5, and this is 150. That's the same thing. It's different textbook, use different abbreviation. It's anionic proteins. Yeah, nope. No, that's a different formula altogether, which we're not even going to bother learning. Called the Goldman... I wish it was Goldman Sachs. It's a GHK, and I can't remember what the H and the K are. It's like Hodgkin and stuff. All right. Now, all we got to do is do a little bit of math here that we're just going to do to give you some numbers to see. All right. And what this does, remember, it tells you where that point is where the chemical and the electrical equilibrium are reached. All right. So just using our numbers, outside the cell it's 150, inside the cell it's 15. So 150 over 15 equals 10. That's why we don't do math. Log base 10 of 10 is 1 times 61 divided by 1. So, for sodium, the equilibrium constant is about 60. All right, so what? Well, that means that the difference in charge between the outside of the membrane and the inside of the membrane, when it reaches 60 millivolts, the movement of sodium has reached equilibrium. Let's do the other one. 5 divided by 150, 1 over 30. Log of 1 over 30, some horrible number. So log of 1 over 30 times 61 over 1 comes out to -90. And for those of you who have a calculator, you can go and do the math and you can see that. So potassium stops moving when the difference in charge between the outside and the inside is 90 millivolts. Now, the positive and negative charge, what does that have to do with? Well, what we're doing is we're comparing the outside to the inside. And so the movement is from the outside in. So when it's positive, that means the flow is going to be going from the outside in. And when see the negative sign, the negative side refers to movement in the opposite direction. Right? Well, how do we know this? Well, look at the formula. Outside versus inside. Right? So I'm always comparing outside versus in. And in fact, you can even cheat and not have to do math. You can just say, oh, when I have more sodium outside than inside, then that's going to favor the movement inside. And when I have more potassium on the outside versus in, that's going to be less than 1, or actually less than 0, because we remember our rules about logs. I don't, but you guys do. And you'd know that's a negative number. Now you're sitting there going, I don't care about this. But this becomes important because what did we say about the environment around the cell? What does it have in it? It has sodium. See, there are no trick questions in this class. All right? It has sodium, right? So potassium is moving down its gradient, presuming, of course, it has channels to do so. Sodium wants to move down its gradient, presuming it has channels to do so. And what happens is that now we're constantly seeing movement because neither of them can ever reach equilibrium. The equilibrium for sodium is plus 60 millivolts. The equilibrium for potassium is minus 90 millivolts. Those two numbers will never be equal because they're two different numbers. All right? So, will sodium ever stop moving into the cell? Will potassium ever stop moving out of the cell? No. Well, when you die, but you're going to reach some sort of equilibrium that meets neither of those criteria. What we're doing, yes. What? Oh yeah, so this has to do with Faraday's constant natural. This one right here. Yeah, so what this number, what we're trying to solve for, which we're never going to solve for, this number tells us the point in voltage when movement of the ion reaches equilibrium. In other words, the point at which chemical equilibrium reaches or equals electrical equilibrium. All right? So there's no more net diffusion of that ion. So, for potassium, the net diffusion of potassium will stop when we have a difference of charge of minus 90 millivolts. Let's go back and look at this picture again one more time, even though it has no millivolts on there. And let's see if I can move this out of the way. When I move that potassium out, what happened on the inside? We got more negative, right? And so we could measure that in terms of voltage. Whatever that single molecule moving equals X number of millivolts. And so each ion of potassium moving out equals another millivolt until ultimately we're going to reach that point where it's minus 90 millivolts. And that next potassium that moves out is going to do what? Oh my goodness, I have to go back. And so it pops back in. And now you've reached equilibrium. That's what that value represents, that minus 90. The plus 60 over here is dealing with the sodium. Now I didn't draw a channel over here, and now I guess I will. So now I have a sodium channel, and sodium will move in, leaving behind its chlorines, which would balance things out. All right? At some point, that next sodium that moves over, which is going to be at 60 millivolts, is going to be, oh no, I've left too many chlorines alone and sad. I have to come back and balance it out. Yeah, you have to give these things a certain degree of sentience. So the idea here is that there is a point when the movement of ions stop moving. And it's at a specific charge or membrane potential. Now, everything I've just shown you here with these values, notice what I've dealt with. I dealt with a single ion. I dealt with a single ion. To get this value was for sodium. To get this value was for potassium. When I drew this picture over here, I dealt solely with the potassium. And then when I drew this picture down here, I dealt solely with the sodium. So everything I just described to you is theoretical. In other words, it's all done in a laboratory. And there's an actual formula that you can use called the Goldman-Hodge, whatever, that actually describes the actual value or membrane potential based upon the number of ions that are moving plus the relative number of channels that are available. So what you say? Well, those relative, let me get back to my slide that I want to get to. I'll get to that in just a second. I've got to pause for a moment to talk about the sodium-potassium ATPase. All right? Because what's going on is every time that we're moving sodium in and potassium moving out, even though we can reach some sort of equilibrium ultimately, we still have our little friend over here. And our little friend is pumping out sodium and pumping in potassium. Right? Y'all agree with that? We've talked about that, right? At the expense of 1 ATP. And so this has an effect on the actual membrane potential, right? Because even though without this we will reach some sort of potential, some sort of value, some sort of voltage at which everything comes to rest, but this thing accounts for 20% of the membrane potential because it's constantly bailing out the boat, as it were. Right? So for every 3 potassium, let's say I move 6 potassium or 6 sodium in, right, and trying to reach my equilibrium. Well, I'm pumping 3 sodium out, so that screws everything up. Does that make sense? That's all you got to know, is it adds to the problem. All right? So I wanted to just kind of bring that up. So what I'm saying is that we can actually calculate this out. We're not going to because, yay, we're not a math class. But what we have to take into account is the relative permeability of the ion. Now, I'm just going to come back over to this little slide right over here where I was writing, and I'm going to give you a rough idea of what the relative permeability is. For every 1 sodium channel there is in a plasma membrane, there's anywhere between 50 and 75 potassium channels. So, if ions are passing through their respective channels, which one do you think has a greater effect on the membrane potential? Potassium. That's right. And so when we're looking at the membrane potential of cells, we can say then that potassium has the greatest effect. In other words, that the membrane potential of a cell is going to look a lot more like potassium than it does sodium. Now again, we're not doing the math. That's that Goldman-Hodgkiss, whatever, Klein, I think, is the third name. I can't remember. But in essence, what it does is it allows us to see what the membrane potential is. It allows us to calculate and see what each of these different little molecules, what sort of effect it has on the membrane potential. And what is the effect? Well, if you look at the plasma membrane of most cells, it's minus 70 millivolts. Now, do you have to memorize that? I'm not going to ask you it. It's kind of helpful to remember it. All right? But what this does is describes everything that we just did. We have tons of potassium here. We have these anionic proteins here. We have sodium here. And we have chlorine out here. We have channels for potassium. We have channels for sodium. We even have channels for chlorine. I'm just making up shape. And then we have this ATPase pump. And what happens is potassium moves down its gradient, making it more and more negative because it's leaving behind these anionic proteins. As it becomes more and more negative, that moves our membrane further and further away from equilibrium from sodium, so sodium starts moving through its channels, bringing it back up. But because there's more of these, this moves out faster, bringing our membrane potential down to a value that's a lot closer to the minus 90. And when that cell is sitting there doing absolutely nothing, kind of like what your brain cells are doing right now, because you're like, please, would he shut up? Your cells are at rest, even though ions are still passing back and forth, but because we have this, to keep that imbalance in place, our cells are really, our neurons are at rest at about minus 70 millivolts. Now, what this means is that means there's energy there that we can take advantage of. Energy that we can use to create signals. All right? Now, what we do is we're going to measure these signals, and we're going to look at them, and we're going to talk about action potentials later. God, this guy's just, everywhere you look. How hard is it to do a nice little polynomial for solving for force? There we go. All right. But what we're going to do is usually you're going to look at the change in that membrane charge, or that membrane potential. And what you're going to do is you're going to see this as a graph. Usually, I'm just going to do it along that. All right. And so, if our membrane potential is at minus 70, what we say then is that our cell has become polarized. So here we are, polarized. Now, why do we call it polarized? Well, any value that's other than 0 is a polarized value. 0 is non-polarized. If you're plus 1, you're polarized. If you're plus 70, you're polarized. If you're plus 1,306,000, you're polarized. If you're minus 12, minus 56, minus 20, you're polarized. You're anything other than 0. And you remember doing this in 3rd grade. Do you remember that? You remember when they gave you those little problems that looked like this? They had the little line, and here's 0, and they said find the minus 3, and you had to go out there and do minus 3. That's polarization. You learn this. So learn the term. Polarized means anything other than 0. Yes? 0.1. 0.1 is not 0. Well, if I told you in this class you have to take out the 5 significant digits, no, you're not going to do any math. So, all right, but anyway, so doesn't matter where we are. If we're down here at minus 70, if we're up there plus 70, plus 30, whatever, we're polarized. When we move toward 0, this is called depolarization. All right, again, if you're way up here, I'm going to put here's 0. If I'm way up here and I'm polarized at plus 30, as I move towards 0, so there's my 0, I am depolarizing. So depolarization refers to moving towards 0. When you return back to your original state, that is repolarization. All right? And then, if you move further away from 0, hyperpolarization. Now, I made a little, if you didn't catch that, there's also moving from a hyperpolarized state back to your original again, and that would be repolarization. So this is repolarization, and this is repolarization, because here we are at minus 70, that's our polarized state, so we're always moving back to where we started originally. All right? So repolarization always means moving back to my original state, my original polarized state. Is that confusing? What's that? Yeah, it's kind of like an unhyperpolarization. All right. Now, these terms you're going to have to get used to because we're going to be using them all the time. And I think I'm probably going to be, that's going to have to be the last thing I talk about. And I'm going to figure out what the heck is going on with this thing when we come back so that we can actually have a real conversation with slides. Before you guys get all happy, are there any questions about the stuff I talked about? I know Chalk Talks go a little bit slower. Is this better? I mean, did you guys feel good? Didn't like it at all? Okay. All right, you guys have a good day. We will see you next time.